Thank you for joining us today, Ethan.
Yeah, thank you for the introduction. So good morning, everyone. Today I'm going to talk about our recent work on enhancing Trino's query performance and data management with Hudi. A bit about myself, I'm Ethan. I'm currently a data info engineer at OneHouse. So OneHouse as a company delivers the universal data lakehouse architecture as a fully managed service. I'm an Apache Hudi PMC member. I drive key initiatives on Hudi on the transaction database layer and engine integrations with Spark and Trino. So before I joined OneHouse, I was a senior engineer at Uber. I was among the first using Hudi incremental processing to build the first kind of near real-time analytics to serve the near real-time network KPI dashboard. So before I start the talk, let's do a quick poll by raising hands. So how many of you know Hudi? Quite some people. So how many of you are using Hudi? Cool. I think I'm actually great to be here to actually tell you more about Trino and Hudi, why they are like a good combination to use. So in this evolving landscape of the big data analytics, it's actually pretty essential to have the efficient data management and retrieval systems and provide the data freshness. So both the query and update performance are important to deliver the fresher data. So if you look at Hudi and Trino, basically the combination of Trino and Hudi serve the exact purpose as a viable option. So Trino, as you all know, provides the fast SQL query with massive parallel processing. And while Hudi provides like the fast upserts with incremental processing in the lakehouse on the cloud. So both of them contribute to the fresher data, reports, and analytics. So in fact, there's a case study where Robinhood adopts Trino and Hudi in their architecture to deliver end-to-end change data capture from PostgreSQL to the data on the cloud for fast analytics and fresher reports with Trino. So you can check out this Trino community broadcast for more details. So in this talk, I'm going to first give a brief overview of Apache Hudi, the open data lakehouse platform. And then I'll talk about how Hudi improves query performance with the multimodal index framework. And I'm going to talk about our recent work on enhancing Trino Hudi connector, and I'll conclude the talk on the future of Trino with Hudi. So Hudi was born in 2016 at Uber when it was going through the hyper-growth mode while moving from a warehouse to the data lake. So the problem Uber had to face were challenging because of the scale and complexity, and demanded designing capabilities such as transaction guarantees on top of immutable storages. So to delve into the use case specifically on this slide, as you can see here, so we have the use case where the trade database change logs would need to be ingested into the raw tables based on the Parquet format. And every 8 hours, the job used to bulk ingest 120 terabytes of data, whereas the actual change itself would be just less than 500 gigabytes. So in this case, the downstream pipelines would be built off this raw layer. And those two needs to recompute all of these like 120 terabytes of data every 8 hours. So the end-to-end freshness would be around 24 hours. So that's kind of not bearable. And the ingestion performance was also extremely poor. And as you can see here, basically, there's a massive waste of resources, compute, I/O, network, et cetera. And there was no control over failure recovery scenarios. And imagine, let's say there's a job failure in this situation. That can cause cascading effects of cleaning up and retraining the jobs, also in the subsequent pipelines along the chain. So when trying to design a solution for this problem, the creators of Hudi kept asking different questions. So questions, for instance, the question can be, can we actually consume only the changes instead of full recompute? Because the changes are only a very small percentage of the whole data. And this would drastically reduce the amount of data and compute needed to ingest every time. And the next question would be, can we design a way to absorb these changes faster into the lake tables? And while the upstream change logs can provide just changes, can we efficiently query just the changes from the lake tables from the upstream? And while all of these are happening, can readers be isolated to not read partial data or dirty data in the tables? So these principles guided the core primitives of Hudi, the absurds, the incremental reads, and the snapshot isolation. So with Hudi, we have this serverless transaction layer with database-like abstractions for DFS compatible storages built. And now absurds took less than 10 minutes to capture, only those like 500 gigabytes of change data. And end-to-end latency reduced from 24 hours to 1 hour. So this propelled more and more use cases, even outside Uber, and Hudi started to evolve rapidly. So today, we look at the ecosystem around Hudi. So Apache Hudi is much more than just like a table format. It serves as a comprehensive lakehouse platform designed for data ingestion and processing. And it's equipped with a rich range of features and serves and the services such as table services, clustering, compaction, and maximizing the efficiency of both reading and writing data. So as you can see here, at the foundational level of this platform lies the data lake storage. This is where all the data resides, stored in prevalent data formats like Parquet and Avro. And this format has been designed for efficiency and scalability, ensuring that all the data is stored in the way that's space efficient and easy to access. And upon this space, we can see that Hudi provides a transaction database layer. And this layer is where Hudi's true power shines, as it offers multiple services, including table services, indexes, concurrency control, with ACID guarantees, among others. And these services collectively offer significant enhancements to data and table management. So for example, table services facilitate the handling of data at scale. And indexes speed up the data retrieval operations, and concurrency control makes sure that there's consistency of data across multiple operations or writers. So after data is successfully ingested from various sources, including like the data streams, databases, and cloud storages, and they are effectively managed in Hudi. So Hudi also offers the ability to connect to connect this process data to popular engines like Trino, Athena, and for different types of analytics, like stream analytics or BI or batch analytics, for example. So by facilitating these integrations, Hudi allows for efficient and advanced querying of data. So on this slide, it shows some statistics from like some big companies using Hudi. So Hudi is already proven at massive scale as a lakehouse platform. And ByteDance, TikTok, Uber, Walmart, and GE all use Hudi for their mission-critical applications. And for example, at ByteDance, Hudi is being used at an exabyte scale for just a single table. And even at this scale, Hudi brings analytics latency from days to minutes as the report. So this is pretty amazing. So as a talk, I'll give a brief history of Hudi. Next, I'll talk about how Hudi improves the query performance with the multimodal index, which is the key component inside the Hudi platform. So one key to improving the query performance is reading fewer bytes. There are three aspects. The first is the indices, which is helpful for locating records with a small amount of index metadata. And this is especially helpful for the queries that look up the needles in haystacks, as only a few selected records are needed to be returned. And the second aspect is the caching. I think it's already been talked about in previous talks. So basically, if queries repeatedly read the same files or blocks, then a read-through cache can help eliminate access to storage and reduce I/O cost. And the third aspect is the storage layout. So imagine that queries fetch records which have already been clustered on storage. That can benefit the query performance because if the data are physically clustered on storage, then it needs fewer reads from the storage by reading the actual records because they are already clustered. And in this talk, I'm going to mostly focus on the indexes, which Hudi shines. So a brief introduction to index, as some of you may already know. So index is widely employed in database systems such as RDBMS and data warehouses to locate information quickly. So this is similar to how you can, for example, locate some information from a book, where the book provides like an index page at the end of it. And in data system, such indexes are used to reduce I/O costs and commonly used to improve query performance. So in Hudi, we already use indexes for various purposes. So we use indexes to locate record efficiently and do fast updates. So as you can see in this diagram, so without index to apply updates and deletes, each data file has to be merged against all of the updates and deletes for the table. However, with index in Hudi, we are able to merge each file with the corresponding updates and deletes for that file only. And this significantly reduces the I/O for merging the data. And in Hudi, we support different types of index, such as Bloom filter-based index, the H-based record index. And to efficiently manage and fetch index metadata in Hudi, the multi-modal index is established. So it's used on both read and write paths for efficient upsert as well as faster queries. So if we look at, for example, what happens behind the scenes when executing a query, the first step involves fetching the metadata, then followed by query planning, applying some optimizations, and then finally reading the data from the files and then serving them to the user. So fetching the metadata is key to improving the query performance. And in Hudi, as you can see here, the multimodal index is structured as an internal metadata table with multiple partitions supporting different types of indexes, such as file listing, the column stats, Bloom filters, and the new record index and functional index column, which I also touch upon later in the talk. And all of these indexes can be built asynchronously without blocking the ingestion, so providing the user a seamless user experience. So we have introduced a new index in Hudi 0.14 release called record level index. So before its inception, for fast record lookup, H-based index, as I mentioned, serves as a record to location mapping. The problem is that a separate H-based cluster needs to be maintained. And H-based is operationally difficult to maintain and actually scale for throughput. So, and also that requires dedicated resources and expertise. So that's why we designed the new record level index. So that comes to the rescue because by design, we make this record level index to store the key to location mapping like H-based index, but directly in the table level metadata. So to realize that, we create a new partition named record index, and we store the mappings in the metadata table. So the index metadata is stored in like a few file groups instead of co-locating with other data files. So in this case, this can drastically cut the cost of file I/O. And another benefit by using this internal metadata table is that the record index can benefit from like fast index update and lookup because the index itself can be pretty big. So the metadata table is actually an internal MR table that can enable fast updates for different index metadata. And the metadata table uses the H file format, which enables fast lookup so that it doesn't have to scan, it doesn't have to read the whole file, but instead scanning parts of the file for looking up the record keys. So here is a brief look at how the record level index metadata is organized on storage and how fast lookup works. So you can see that this new record index partition is created in metadata table, and there are few file groups organizing all of these key to location mappings. And we store the mappings in the H file as I mentioned. So let's say we have a set of record keys to look up. Then first, what happens is that the corresponding file groups are identified by like a pretty fast hash functions. And then these keys are looked up in the H file through the point lookups without having to scan the whole file. And if there are updates, then we have this log appending mechanism. So we also store these updates in H file data block in the log file. So you can also enable point lookups. And we have done a few performance benchmarks on both read and write on Spark to demonstrate the performance benefit of record index. So in the first case, we have 1 terabyte table, and each write batch is 200 megabytes of random updates across the table. So the update percentage is pretty small. We compare the performance of record level index with the global simple index, which is best for random updates before a record level index is available. So we can see that the index update or index lookup latency is reduced from around 20 minutes to 1 minute after using record level index. This is because record level index only has to read metadata from a few file groups in the metadata table, while global simple index has to scan all of the data files, which is not efficient. And this contributes to 2x improvement on the overall write latency because the savings from the index lookup offsets the small additional overhead on updating the index itself inside the metadata table. And see, okay, cool. So next, we also measure how record level index improves the SQL query performance with point lookups. So we use the store sales table in the TBCDS 10 TB datasets, and we run 2 types of query, the select star for a particular record key and delete operation for a particular record key. So by using record level index for filtering, as you can see here, we see 2 to 3x improvement with the record level index compared to no record index. This demonstrates how record level index can give a great performance benefit. We actually have written a blog on how Hudi's blazing fast index for large-scale datasets are enabled through record level index. Please check it out. All right, so as I talk about how Hudi improves performance through this advanced multimodal index, next I'll talk about how we enhance the Hudi support on Trino with the Hudi connector to be able to use these indexes. So a big history of the Hudi support in Trino. It started in the Hive connector where the Hudi query support is integrated through the Hive input format implementation. So all the major query types, including COW, MOR, read-optimized, snapshot, and bootstrap queries are supported. And Hive connector is actually later deprecated since Trino version 4.11, which redirects the query to the new Hudi connector. We have introduced new Hudi connector supporting COW and MOR read-optimized queries since Trino version 3.98. So while we are working on bringing more query type support, Trino was undergoing the dehadooping and changes around file system. So the metadata-based file listing is no longer supported since version 4.19 because the metadata table reading requires HBase and Hadoop dependencies at the time. So to actually better support Hudi Trino connector, Trino Hudi connector, the Hudi community has introduced new abstractions and made major refactoring and changes in the recent Hudi 0.15 release by revamping its reader core. So with that, we are bringing all major query support, including read-optimized snapshot and bootstrap queries in the upcoming Trino releases. So next, I'll talk about how Hudi 0.15 release unlock all of these new features. So at its core, the Hudi 0.15 release introduces two new abstractions. So the Hudi storage abstraction provides the Hadoop independent file system and storage APIs for Hudi readers and writers to work with. And the Hudi storage is extendable with Hadoop file system-based implementation to support like Spark and Flink engines. And also, we newly introduced the Trino file system-based implementation for Trino Hudi connector. And the second abstraction we introduced is the Hudi IO Factory, which provides the APIs to create readers and writers for input and output without depending on Hadoop classes. So in this way, we make Hudi common module and core reader logic in Hudi Hadoop independent. So this makes engine integrations with Trino much easier and more maintainable by plugging in custom storage and IO Factory implementation. So the other challenge is we need to support metadata table read with HFile. So to do that, we introduced a new HFile reader in Hudi 0.15 release. So we have also written a HFile format specification that defines the HFile format required by Hudi to enable fast point lookups. And these allow HFile reader and writer implementation in any language, for example, in C++ or Rust, by following this spec. And inside 0.15, we have implemented a new HFile reader in Java, which is independent of HBase or Hadoop dependencies. This HFile reader is backwards compatible with existing Hudi releases and storage format. And the new Hudi connector implementation uses this Hudi reader to support reading different indexes in the metadata table. So by putting all this together with all the new abstractions, we reintroduce the Hadoop independent Hudi common module as dependency for the Trino Hudi connector, so that rich feature set in Hudi reader core is now available in Trino. And this also makes Hudi support maintainable and easily evolve with future storage format changes. And the Hudi storage abstraction also unlocks future optimization opportunities, including Alluxio caching. And with the new HFile reader implementation in Java, we bring back the metadata-based file listing, which is loved by Hudi users a lot. So through our TPCDS 1TB benchmark based on our Trino Hudi connector feature branch, we observed 38% query latency reduction when using a metadata-based file listing in our Hudi connector. And with the custom Hudi Trino IO Factory implementation to support custom readers and writers, we added a new Hudi snapshot directory lister that supports the MR snapshot query, which is not available before. So now, with all of these features available in our feature branch, we are in the process of upstreaming these changes to the Trino community. So as I talk about all of these great existing words, so how does the future look like for Trino with Hudi? So the Hudi community has actually a bold vision for our next big release line, the Hudi 1.x. So we have been adding new capabilities in the 0.x release lines like 0.15 and potentially a new 0.16 release. But we can also turn the core of Hudi into a more kind of general purpose database experience for the lake. So as you can see the code here, we actually reimagine Hudi as a Hudi 1.x, the transactional database for the lake with polyglot persistence, raising the abstraction and platformization even higher for Hudi data lakes. And actually, in fact, if you look at the diagram comparison here, Hudi already provides functionalities like access method, the log manager, utilities and services that are core components in a database system. So on the left side is the kind of the main components of a RDBMS from like a pretty famous paper. You can see in this, on the left diagram, there are like client communication manager on the top, process manager, relational query processor, transactional storage manager at the bottom, and the share components and utilities on the right side. And you can see that on the right side, we re-envision the Hudi 1.0. And this is how Hudi provides the building blocks and interacts with different engines. So different engines like Spark and Trino bring components in blue. And then Hudi will be adding new components and yellow to enhance existing components. And to the particular interest to Trino as a query engine, Hudi has pretty deep integration with Trino. And the components like query optimizer and plan executor components will use Hudi's advanced indexes to do more optimization for query performance on Trino. So I'll quickly touch upon a couple of even new indexes we are adding in 1.x, and they are already available in 2 beta releases. So the first one is the functional index. So functional index enables users to create indexes on functions or expressions. So on the high level, the concept of functional index is pretty simple. So just like how you can create an index on a column, functional index allows you to create an index on a function of a column. But the efficacy of the functional index goes beyond what a simple index can do. So let's consider a case where, for example, on this slide, basically the raw events are ingested from the microservices. Each event contains like an org ID and a timestamp. So most queries on the table are organization specific and also fetching logs for a particular time range. So you can imagine that the user may attempt to physically partition the data by both the org ID and a timestamp or day string of the timestamp. So let's say the cardinality of the org ID is 1,000, and we have 1 year of data. This kind of partition scheme can lead to like 365,000 partitions, which is pretty large. And because in most cases, the data is skewed based on the organization, most orgs may have fewer data, but only a handful of orgs having majority of data. Such partitioning scheme can lead to many small files, which are not good for query performance. So by using a functional index, actually even with the mix of old and new partitioning scheme, we should be able to effectively skip data based on the range of data string for each file, regardless how files are stored under different physical partition paths in the table. So this leads to the profoundness of the functional index that it actually absorbs the partitioning with indexing or the index metadata. And there's no need to hide or evolve partitions in this case. And another good index we introduced is the secondary index. So it provides the index metadata on non-key fields to improve the query performance with predicates on such field. So the secondary index allows users to do point lookups on non-key fields efficiently. And here is our roadmap on pushing the next Hudi 1.x release line and while maintaining our existing 0.x releases, along with contributing our work to Trino Hudi connector. So the 1.0 beta 2 release with the secondary index and improvements to metadata table will soon be available later this month. And we are going to make 1.0 generally available in Q3 this year with the new storage format finalized and automated upgrade experience from 0.x tables. And we'll also provide a 0.16 release as a bridge release to make the migration from 0.x to 1.x much easier. So we want to make 0.16 to be able to read both the 0.x and 1.x tables with so much advanced indexing capabilities. And on the Hudi 1.x release lines, we are going to also support new indexes beyond secondary index and functional index, and also support unstructured data vectors and vector index. And while we are doing that, we are going to contribute our work to Trino Hudi connector with the query support. And we are adding Alluxio-powered caching and other index support and integration with Hudi 1.0 in Q3. And without such abstractions, the DML and DDL support will be so much easier. And then the support in Trino Hudi connector is under discussion. So as I mentioned, Hudi is pretty much community-driven, so we love new people to come join us and build new features. And here are all the resources you have. The slides will be available later. And here is also the QR code you can scan to join our Hudi Slack to ask questions. And before I conclude the talk, I also want to quickly touch upon what OneHouse does. So OneHouse actually delivers the universal data lakehouse architecture as a fully managed service on top of open source Hudi. And you basically get automated ops-free lakehouse experience with all of the table services such as clustering, compaction, small file handling, catalog syncing, and scaling table metadata, and all of these multi-modal index I talk about. And basically, data go to bronze and fast and silver with incremental processing. And also with Xtable as its core, as you can see here, we support all three formats. And you're never going to be locked into one single lakehouse format. So with that, thanks for your attention. And I'd like to take questions from the audience.
Yeah, thank you again, Ethan. That was amazing. It's great to see how much innovation you're pumping into the system and how much usage it's getting, and like how much it's evolving to be like, it's basically going to be a database all over again. Yeah. And everything is going to be transactional, really good. And it's just an implementation detail that there's a lake underneath. It's like really, really cool. Do we have any questions from the audience? And who's wanting to try out Hudi next?
Hi. Building the index, I saw that you had a statement for creating. I'm guessing it's in Spark. But keeping the index in consistent with the current state of the table, does this mean that inserting into the table is also dependent on updating the index? Thank you.
Yes. So in Hudi, you can create index using SQL, and the index will be initialized in the internal metadata table. And then you can keep the index updated with the ingestion pipeline. So let's say if you, or like even like DML or DDL. So once the data is basically written to the table before committing to Hudi table, we also automatically update the same kind of index metadata. And we have this support in Spark. In Spark data source and DML and DDL, I think the right support in Trino hasn't been finished yet, but that's our roadmap.
Great talk. I have a question. So you mentioned you support Spark and support Trino. How do you deal with the functional indexes across engines, given that you have function definitions that may not be available or may have different semantics in different engines?
Yeah, that's a good question. So we maintain the functions we support in Hudi, and then we also make it like engine agnostic. And we have a layer where like, for example, we support a core set of functions like date of TS or some common UDFs. And those are transformed to like engine-specific implementation like Spark, Presto, Trino, or like even Flink. So, and then we maintain this functional index metadata inside Hudi. So we know like which function to apply and how to actually use that in query engines.
That's very interesting, and I think it's also one of the aspects that is like emanating everywhere, that a multi-platform and multi-query engine world is a reality, and like the efforts of the table formats to like really support and understand that there's these issues where you need to kind of like be able to support all of them is great, and I love seeing how Hudi is like stepping up and really getting this into Trino.